Hello, and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at a short introduction to the concept of cross-correlation. So far we've spent quite a bit of time talking about autocorrelation being a quantitative measure of the similarity of a function or a random process to itself at some earlier or later instant in time. Cross-correlation allows me to compare quantitatively the similarity of two functions at earlier or later instances in time. We're not going to go into nearly as much detail with cross-correlation as we have with autocorrelation, but I do want to touch on it a little bit. So, cross-correlation. So, for example, maybe I'm interested in this. Maybe I've got some sort of system. Might be a linear system, might be a nonlinear system, who knows. Just some sort of electrical system. And at the input of my system, I have a random process X, and at the output of my random process, at the output of my system, I've got a random process Y. And I might be interested, for whatever reason, on how X and Y relate to one another from a statistical perspective. And cross-correlation will allow me to get access to some of that information. We're going to assume that my random processes We're going to assume that my random processes X of t and Y of t are at least are individually can't spell. individu. Individually wide sense stationary. And also at least wide sense joint stationary. Now, I'm not going to get into a lot of detail on joint stationarity, but all that means is, in the wide sense, that the statistical relationships of X and Y up to and including the second order statistical value being cross-correlation, for example, joint stationarity means that X and Y are jointly stationary in their statistics at least up to the second order. I'm not going to get into too much detail with that, but that's what that means. All right, so remember, autocorrelation looks something like this. All right, so we're assuming that X of t is at least wide sense stationary. And if X of t is also at least wide sense ergodic, that equality applies. I can either calculate the autocorrelation using ensemble averaging or time averaging. All right, just a reminder. So what does cross-correlation look like? For joint stationary processes, X and Y, cross-correlation looks like this. We subscript it with both x and y. It's a function of an absolute shift parameter tau, and it's going to be the expectation of x of t times y of t plus tau. Okay? That's what that is. All right, I just replace one of the x's with a y. And as with autocorrelation, this is a measure, a quantitative measure of similarity. Quantitative measure of similarity of x compared to y at some later instant in time. Okay? Let me give you some special cases. One, if x of t and y of t are what we call orthogonal, if x of t and y of t are orthogonal, then the cross correlation is always and everywhere 0. Okay? If x of t and y of t are orthogonal, then the cross correlation is always equal to 0. Another special case. If x and y are statistically independent, and individually stationary, and jointly stationary as well, then my cross correlation equals, remember, if I have statistically independent processes, then the expectation of the product is the product of expectations. So I get this far because they're independent, statistically independent, but they're individually and jointly stationary. So this means that I can drop the shift parameter tau, and then that's just the mean of x times the mean of y. Okay? So statistical independence does not necessarily mean orthogonal. Okay? If I have statistically independent random processes, at least one of which has 0 mean, then my processes are indeed both statistically independent and orthogonal. But orthogonality doesn't necessarily mean statistical independence and vice versa. All right. Some properties of autocorrelation, or excuse me, cross correlation. Properties. 1. My cross correlation of when I subscripted x and y, where I'm saying here that y is what is shifted relative to x, I can also define this I can shift x relative to y okay. So just thinking about the concept of relativity, if I shift x to the left, that's the same as shifting y to the right and vice versa. So hopefully you'll see that when I subscript it this way, the cross correlation x y of tau equals r subscripted yx evaluated at minus tau. In other words, these two relationships, those are both cross correlation terms. They are mirror images of one another around the tau equals 0 axis. Okay, they're mirror images of one another about tau equals 0. That's the first property. Second property, I'm not going to prove this, I'll just state it. The absolute value of my cross correlation is always less than the square root of the product of the autocorrelations, or normalized powers, autocorrelation evaluated at 0, which is my normalized power. Okay? Just stating that, not proving it. Another one is that my cross correlation is always less than or equal to the sum of normalized powers. Alright, autocorrelations evaluated at 0 are normalized powers. And it's not really a property, but I'll state it as such. Cross correlation is, in almost all cases, not an even function. All right, the autocorrelation, as we've discussed in the past, is always an even function. If I take a function x and shift it to the left or shift it to the right, I get the exact same autocorrelation result. The only way I'll have a cross correlation that is even is if both random processes x and y are both even. That's not commonly the case. Okay, so just some properties. Let's do some examples. All right, so let's assume that we've got a linear system with a process x at the input and y at the output. Okay? One of the properties, or the defining properties of a linear system, are that, one, I can only change the amplitude of particular frequency components, and I can delay particular frequency components. So let's assume that my input random process is a single frequency tone with amplitude A. This is my handy-dandy random process where I'm creating a random process by embedding a random variable in a time domain function. So capital theta is a random variable uniform on 0 to 2 pi. All right, that's a single frequency random process. A linear system, when I apply a single frequency tone to the input of a linear system, the only thing I can do is change its amplitude. I can amplify it or I can attenuate it. I can attenuate it all the way to 0 if I want. I can amplify it or attenuate, change the amplitude, and I can delay the signal through my linear system. So my output random process will be some new amplitude B, cosine omega naught t plus capital theta, my random variable, plus some fixed delay. So this will be a constant phase shift. Due to the system delay. Okay? And the amplitude changed. All right, that's what a linear system can do to a single frequency tone. Well, the autocorrelations, excuse me, the autocorrelations of both X and Y look something like this. We've seen that before. We've done that many, many times. Similarly, all right, the autocorrelation for Y is the exact same form as the autocorrelation for X. The amplitude changes, but the dependence on shift parameter, the dependence on the shift parameter the dependence of my autocorrelation on tau, my shift, is not a function of my initial phase. So therefore, it's independent of little phi. All right. So if I've got a sinusoid random process, as we have for both X and Y, the autocorrelation is independent of any fixed constant, any fixed phase constant. All right. All right. What's the cross correlation of these two random processes then? That's my cross correlation. Let's plug everything in. All right, plugging in X and Y, I get that far. All right, simplify this, and I get AB over 2 times the expected value of cosine omega naught tau plus phase plus cosine omega naught 2t plus tau plus 2 theta plus phi. And here I've used the trigonometric identity, cosine A cosine B equals 1/2 cosine A plus B plus 1/2 cosine A minus B. In case you've forgotten that. You'll also recall that the expectation of the sum of two random processes equals the sum of expectations. Next thing we'll notice is that this random variable is uniform on 0 to 4 pi by virtue of that factor of 2. So my second, inside of my square brackets, my second cosine function goes through 2 full cycles. So the expectation of that second term goes to 0. All right? And you'll also notice that this thing is non-random. All right? My random variable, capital theta, doesn't show up in this first cosine term. All right, so my autocorrelation, my cross correlation result is then AB over 2 cosine omega naught tau plus phi. Okay? All right. Well, that's not an even function because it's not centered at the origin. The peak, the central peak, occurs when omega naught tau plus phi equals 0, or omega naught tau equals negative phi, or my shift parameter tau equals negative phi over omega naught. That'll be in seconds. All right, so by virtue of the minus sign here, we'll see that the central peak of this autocorrelation is shifted to the left. Shifted to the left in tau. Okay, it's shifted a bit to the left in tau. Okay, well, what about r sub yx? What's that look like? Well, r sub yx of tau equals the expectation of y of t times x of t plus tau. And we know from one of our earlier properties that it's the mirror image of r x y of tau. And so that's going to be a b over 2 cosine omega naught times minus tau plus phi. Pull out a minus sign, and remembering that cosine is an even function, I get a b over 2 cosine omega naught tau minus phi. And this will have its central peak at tau equals plus phi over omega naught. So this will be shifted to the right in tau. Okay? Not an even function. Cosine generally is an even function, but when I embed a constant phase delay, little phi in there, the result is not an even function. Okay. Simple enough. Let's do something slightly more complicated and maybe a little bit more interesting. What if I have an adder. Okay? And I have two random processes at the input. X of t and y of t. And the output random process, z of t equals x of t plus y of t. All right? What I'm interested in is finding the autocorrelation of the output. Oops. That's the autocorrelation of the output. How does that, what's that look like? Well, let's plug in what z is. This will be the autocorrelation of just plug in what z and z of t plus tau look like. Z is just x plus y, and z of t plus tau is x of t plus tau plus y of t plus tau. All right, do all the cross multiplies, and I get the expectation of x of t plus tau plus y of t plus tau plus x of t y of t plus tau plus y of t plus tau. All right. And then we keep in mind that the expectation of sum is the sum of expectations. And we get the autocorrelation of x plus the autocorrelation of y plus two cross-correlation terms, r x y plus r sub y x. And then one more step, I get the autocorrelation in x plus autocorrelation in y plus r x y of tau plus the mirror image r sub x y of minus tau. Okay? Now, let's keep in mind that autocorrelation is always and everywhere an even function. So this guy has to be an even function. All right. Autocorrelation of x is even. That's good. Autocorrelation of y is even. That's good. If I take any function and add to it its mirror image about the tau equals 0 axis, this results, the sum results in an even function. This guy's even. This guy's even. And the sum of the two cross-correlation terms, when one is the mirror image of the other, is an even function. So that's good. We expect autocorrelation for the output function z is going to be an even function. All right. Let's go to the next page and look at some special cases. Let's remind ourselves for the adder that my autocorrelation result is that was my result. That's my general result. So some special cases. One, what if x and y are orthogonal? That means that their cross correlations are always and everywhere 0. If x and y are orthogonal, then the autocorrelation of z is just the sum of autocorrelations. Moreover, the normalized power in the random process at the output is just the normalized power in x plus the normalized power in y. Powers just add. Okay? The powers just add. If x and y are orthogonal, this gives us what we call a completely incoherent process. Okay? I'm an optics guy by trade. I talk a lot about coherence theory, incoherent processes, and coherent processes. Not going to get into a lot of depth here, but let me just say that flashlights are incoherent. If I take two flashlights and I shine them on the wall at the same time in the same spot, I just get a doubly bright spot. Let's assume that the flashlights are identical. All right, I take two identical flashlights, both powered by the same number of batteries, and I shine them on the same spot on the wall. I just get a doubly bright spot because those flashlights are completely incoherent. Okay? Not going to get into a whole lot of depth there, but that's an example. All right? Let's look at a fully coherent process. All right? If x of t equals y of t, we get a fully coherent process. We get fully coherent processes, and so what I end up with is my cross-correlation terms become autocorrelation terms, and my result is then four times my autocorrelation of either x or y. All right, my cross-correlation terms become autocorrelation terms. My autocorrelation terms are always even, meaning that they are mirror images of one another about the tau equals 0 axis. And so my autocorrelation for z just becomes 4 times the autocorrelation for x, or 4 times the autocorrelation for y. Likewise, the normalized power in z becomes 4 times the power in x, or 4 times the power in y. There's some synergy going on here. The whole is more than the sum of the parts. Now, I'm not going to get anywhere close to addressing this fully, but a laser is a fully coherent optical source. If I use a beam splitter and split a laser beam into 2 different directions, and later on add those laser beams back, I get 4 times the power in the individual beams. The reason being that a beam splitter is what we call a field splitter or an amplitude splitter and not a power splitter. Again, I'm not going to go into any detail on that, but when I have fully coherent processes and I add them together, I get some synergy in the output relationships. I get more power out than the individual terms themselves carry. All right, in general, if I have a partially coherent set of processes, we get this. The normalized power in Z equals the normalized power in X plus the normalized power in Y plus 2 times the cross correlation function evaluated at 0. All right? This thing, the cross correlation evaluated at 0, is a measure of mutually coupled power. Mutually coupled power. Okay? So I always say that, Jack and Jill go up the hill to fetch a pail of water. Well, maybe they each carry down their own pail, but they might share a third pail. All right? The sum is, there's still some synergy here, but not quite as much synergy as when I have a fully coherent process. The whole is more than the sum of the parts. There's some mutually coupled energy or power shared between the two processes when there's at least partial coherence, but it's not quite equal to 4 times the power in either of the individual processes. Okay? So like I said, my goal today was to just give you an introduction to the notion of cross correlation, and that is indeed all I have to talk about today. As usual, if you have any questions, please contact me at your earliest convenience, and I'll be happy to answer your questions as fully as I am able. That's all. Have a nice day. Bye-bye.